Hello and welcome to our presentation on normal numbers. Our task was to try and discover and find out as much as we could about normal numbers. So you're probably thinking to yourself, well, what is a normal number? Maybe you're just thinking it's the digits 1, 2, 3, 4, which are whole numbers or integers. Well, a normal number is probably not what you think it might be. A normal number is known as a mathematically perfect number. It is basically a decimal with no repeated sequence of digits. It is a real number where no digit or combination of digits occurs more frequently than any other. So each digit 1, 2, 3, 4 each occur the same amount of times. Normal numbers will go on for an infinite length and never repeat the same pattern. An example of a normal number would be 0.12345678910 and so on until infinity. The number below this, which is shown on the screen, is not a normal number. This is because every second digit is a 4. So the digit 4 occurs much more frequently than all of the other digits. So to understand much more about normal numbers, the knowledge of bases is needed. So what are bases? Well, in mathematics, there are many different ways of counting, such as bases. A base is the different number of digits used when counting. So we usually use denary, which is base 10. This contains the digits from 0 to 9. This means that we have 10 digits to represent and make all of our numbers. Computers usually use binary, which is base 2. This contains the digits from 0 to 1. Numbers can also be converted between bases. For example, the number 4, which is in base 10, converted to binary, which is base 2, is 100.
So the properties of normal numbers. There are many surprising and unusual properties to do with normal numbers. Using the Lebesgue method, it has been proved that almost all real numbers, so that's integers and decimals, are normal numbers. It has also been proved that any positive number can be made from the multiplication of two normal numbers, and that dividing any positive number by a normal number will almost always give a normal number as the answer. Normal numbers are said to be closed under finite variations, which in human terms means that adding, changing, or subtracting any finite number of digits in a normal number leaves it normal. Normal numbers often have been used in cryptography. Ciphers and hashes use randomized digits in order to conceal them, and normal numbers are ideal for this. The randomized digits can be created from taking any part of a normal number. The NSA, the National Security Agency of the US, used numbers such as root 2 and other root primes in the SHA algorithms to create unique hash codes. Whilst root 2 and other root primes haven't been proven to be normal, it's widely believed that they are. Simply normal numbers are similar to normal numbers in that each digit occurs the same amount of times. However, unlike normal numbers, the same sequence of digits can repeat, and so they can be rational. For example, the simply normal number 0.123456789 repeating is simply normal in base 10, but can also be expressed as the fraction seen in the PowerPoint, which is a rational number. Simply normal numbers don't have to be simply normal in other bases. For example, 0.1010 in base 2 is simply normal, but is equivalent to 0.6 occurring in base 10, which isn't simply normal as it only contains the digits 6 and 0.
Hello, I'm Ewan and I'm going to be talking a little bit more about simply normal numbers and why normal numbers can be rational. So, normal numbers can't be rational, as by definition they must have the digits 0 to infinity occur with the same frequency, they must never repeat, and they must go on for infinite length. If a number is rational, eventually it will either terminate or repeat. The proof of this can be seen in our poster. However, simply normal numbers can repeat, and because they need only the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to occur with the same frequency, they can be rational. Some examples of these are on the board behind me. The first example is 0.234567891 recurring, and the second example is 0.123456789 recurring. Both of these numbers are simply normal, as when expanding to infinity, the digits will have exactly the same frequency.
Hi, my name is Maria and I'm going to be discussing normality and bases. Let's say that B represents any normal number, and then x is an existing number. Consider a number that continues forever as x in the base B. If this number is simply normal, then we can say that x is simply normal for base B. If x can also be called a normal number if it's normal in base B when B is positive. On the slide here, we can see Copeland-Erdős constant. This is obtained by linking prime numbers in the base 10, which is the usual base used. This was proven to be true by Dirichlet's theorem that states that any even integer can be obtained by adding primes with a maximum of 6 primes needed. This is normal in base 10, as proved by Copeland and Erdős in 1946.
Hello, I'm Alex, and I'm going to be discussing whether or not pi is normal and whether numbers can be normal in multiple bases. Pi is the ratio between the length of the edge of the circle and the longest straight line in the circle. It's an irrational number, and within the community of normal number enthusiasts, it's commonly believed that pi is normal. However, nobody has proven this. If pi was random, then the chance of the example that's on the board up there occurring would be 0.08%. Pi has also been calculated up to 6.5 billion digits, and so far it's looking like it is normal. Real numbers. Most real numbers are normal. Normal numbers can, in fact, be normal to multiple bases, and numbers that are normal to bases 2, 3, 4, and so on to infinity are called absolutely normal numbers. E. Borel proved their existence, and in doing so also proved that most normal numbers are absolutely normal. Chaitin's random constant is an example of an absolutely normal number. However, it's non-computable, which means I can't show you it today. However, it's represented by the symbol omega there. Pi, root 2, and e are all constants that may be absolutely normal, but again, it's not been proven.
So I'm going to be talking about simply abnormal numbers. A simply abnormal number is pretty much like a simply normal number. However, one of the digits does not occur. So this means in base 10, the numbers will appear with the frequency of a ninth. For example, the number up on the board there is 0.1235678, where that block repeats forever. Here the number 4 is missing, so that would count as a simply abnormal number. There's also a local person who's involved in normal numbers. This is Professor Champernowne. He was born 15 miles southeast of Exeter on the east coast of Devon. He was an English economist and mathematician and attended Cambridge University at the same time as the famous mathematician and cryptanalyst Alan Turing. During World War II, he was drawn into the statistical section of the Prime Minister's office to help Winston Churchill make his important decisions. But more importantly for us, he came up with this normal number. This is pretty much the basic form of a normal number, which has all the numbers from 0 to infinity, all in a decimal expansion, and it's a pretty complex formula just to have all the numbers in one formula.
This brings us to the end of our presentation. We would like to thank Peter Ashwin for setting us this challenge and Luke from Exeter University for helping us. Thank you for listening.